All right, so thanks very much for the invitation to speak here today. My group's recently been focused on a question that I think is broadly relevant to chemistry and physics, which is how much time does it take for a certain amount of energy to be dissipated as heat? And we've made some progress on this recently, developing thermodynamic speed limits that we think are beginning to answer this question. And these particular speed limits are interesting in part, I think, because of their connections to quantum dynamics that I want to point out, and very recently also nonlinear dynamics. So I'd just like to briefly share my perspective and some of our more recent speed limit results. And what I'd say motivates them from the top down, at least, is matter that's capable of existing in some dynamical states and capable of performing useful functions. And we see examples of this in biological matter, where broadly we might classify a variety of the behaviors we see in biology under the broad function I'd call structure formation. But this might include the ability of neurons to transmit signals, the ability of systems to sense and respond in this way, but also the growth and replication of structure, or its ability to reconfigure and adapt, like we might find in cellular materials where microtubules can rearrange and control the structure of the cell. And so structure formation, I'd say, is one place that I think one particular type of function we're interested in. Another more recent is the generation of work, which, like structure formation, has to be often be done on particular timescales to be useful. And here we can see examples in the capture and conversion of light and how it's turned into ATP and used for future chemical work, but also how that ATP can be used by biological motors to contract muscle. So it's these examples where work can often have to be done in a very noisy thermal environment, and it can have to be done on particular timescales, like I said, to be useful. And so these types of dynamical functions are particularly interesting and inspiring from biology because they're now making their way into material science and materials chemistry, where there's the ability to create nanostructured materials that have a variety of nice static properties. And the challenge that I think is coming about is the ability to transition from looking at static properties to begin to think about how to implement these dynamical functions in materials. And this has a variety of, there's a variety of behaviors these types of materials can exhibit. We can see them self-organize, but also now heal themselves or annihilate or even replicate. And this example on the right-hand side is a synthetic system where a set of antagonistic chemical reactions drives the formation of the structure. And what you can see is that there's a fibrous material that forms. These fibers grow, but they also stochastically collapse and die out, sometimes simultaneously or next to one another. So there's a flow of energy, chemical energy, that's driving the formation of the structure, but it only happens on a particular time scale. And so the question is, how do we control the flux of energy to precisely time the formation of the structure that can have implications for a variety of other fields? So we want to figure out how to tune the currents and control the timing and in order to better understand and use these types of dissipative materials. So the question that we're asking is, how much time will it actually take to generate a certain amount of energy, for that energy to be dissipated as heat? And this is what I think is a particular, one of the central problems of thermodynamic speed limits, but thermodynamic speed limits, I'd say, on observables. So I'd like to divide my comments between two topics we've been working on, one more focused on the dissipation of energy, the thermodynamic costs, I'd say, and another on the thermodynamic benefits in mechanical work. And to do this, I'll just set up a basic system. We only need a minimum of stochastic thermodynamics actually to do this. But we imagine defining a system that's potentially microscopic and subject to some external drives that's going to execute a dynamical function, but also produce some waste. And that waste might be heat, but it might also be material. So we'll assume that this system, whatever it may be, for the moment, it won't matter too much, has a discrete set of states that are going to represent physical states of our system that we're interested in. So it might be a collection of monomeric units that can assemble into a misbound structure or some preferred optimal structure, say, just to give you an example. And from here, we're going to use tools of stochastic thermodynamics to define some observables. So the internal energy, for example, or the Shannon entropy as another, over some potentially non-equilibrium distribution. And one thing I'll point out here with the Shannon entropy is that, of course, it's well known to this audience that it can be defined as an average over a measure of information. It's sometimes called the information content or the surprisal. And this is going to be particularly significant to the development of the thermodynamic speed limits. And here I'm using thermodynamic speed limit in somewhat of a broad sense, that we're interested in the bounds on time. And I've seen it used as a bound on the time required for a classical system to evolve between two distributions. And we're thinking of it in a slightly adapted way, where it's the time required for an observable to change by a given amount. And we've been thinking about this for a particular set of speed limits that actually look like classical uncertainty relations. So the setup for the physical system will be the space of probability distributions, what's sometimes called a statistical manifold, where we imagine that we've got a system with this discrete set of states and it's evolving continuously in time through this manifold of states. So the dynamics, whatever those stochastic dynamics might be, evolve the system on a trajectory along this manifold. So alongside that picture, there's also a space of observables, whatever chosen observable we're interested in. I'll focus on the energy to make this concrete and easy. But because the system can be subjected to work, the values of these variables associated with each of our states can also evolve. So what we recognized a few years ago was that in just writing down the equation of motion for different observables, I'll use the first law as an example. That we can write down the rate of change of some mean observable, and that this of course has two terms, which are well known to be the heat and the work rates in the stochastic first law. But what we recognized was that the heat term can actually be rewritten as a covariance, so a measure of the linear correlation between the energy states and the rate of change of the surprisal or information content. And this looks a bit like a Liouville type equation or an Ehrenfest's theorem, where the covariance is identified in this case as the heat. So it's this connection to us that was quite surprising and interesting, because information's been discussed, of course, in the context of statistical physics for some time, but mostly in the context of the second law. So it was surprising here to find it embedded in the first law. So this is going to be useful to us moving on, but we can actually, I'll mention as an aside here, we can actually identify a number of other observables as covariances. Anything that has the same form as Q dot here in this equation. So if we take a particular observable, say we take the energy, we can ask a question about how much time it will take to actually change the mean observable by a certain amount. And we can choose what that amount is, but a convenient choice turns out to be the standard deviation in the energy, say. So this is a condition we're interested in. And we can write this change in the mean in terms of an integral over our rate, of course. And if our distance is, our standard deviation here is small, or our time scale is sufficiently short, or our rate of change of the energy is constant, we can pull this out of the integral and motivate the definition of a time scale here that's specific to the internal energy. So it's specific for an observable, but we can rearrange this outermost condition here and define a speed associated with the internal energy. Now we can follow a similar logic, of course, and define the speed associated with the rate of change due to heat. And work was a bit of a sticking point, but is one that we've been thinking about more recently. So I'll come back to this one. So an important thing is we've now got some thermodynamic speeds, in a sense, speeds associated with different observables. And we went back to we can go back to the statistical manifold where our dynamics are evolving along some particular trajectory. In my group, we've been using this idea of the Fisher information connecting to information geometry for some time. Our first work, starting in 2013, 2014, somewhere in there, actually adapted the Fisher information for the purpose of chemical kinetics. So we drew upon some of this history, and which is just the recognition from information geometry that if you change coordinates on the statistical manifold from the probability simplex, so moving from probabilities to what we might call probability amplitudes Q here, our dynamic still evolves the system along a trajectory between two distributions. But these coordinates have a very interesting and important speed associated with it. If we look at the distance between two distributions on this manifold, the speed associated with moving between two distributions, we can write that down using the L2 norm of the rate for our probability amplitude Q, and rearrange this. And we can see that embedded in here is the mean squared surprisal rate. And since the mean of the surprisal rate is actually 0, this is just the variance in the surprisal rate. And this is often defined as the Fisher information. So this is connected to the Fisher metric, which is what gives us a rigorous definition of distance on these manifolds. But for us, we were interested in this quantity parameterized by time, because it's got the dimensions of inverse time squared. So we started thinking, well, this could be a potential intrinsic speed that we could use for a bound on these different thermodynamic speeds. So we can see that this is also a measure of how unsteady the dynamics are, since our surprisal rate's going to vanish when the probabilities are stationary here. So if we put all these things together, we can recognize again that our rate of change associated with heat is actually this covariance. And then we can use Cauchy-Schwarz, or the covariance inequality, as it's sometimes called in this context. And that gives us an upper bound that's got the product of two variances. So this is a classical uncertainty relation. It's got the same form as those in quantum mechanics. But stuck in here is the standard deviation of the surprisal rate, which, like I said, is the Fisher information, here the square root, and the standard deviation of the energies. So this was a result that we realized, well, we can rearrange this and use the definition of these thermodynamic speeds, like the one associated with heat, and write this as a time information uncertainty relation. So this is saying that the Fisher information is a bound on the rate at which energy changes as a result of heat transfer to and from the system. But because the Fisher information, or its square root in this case, is an intrinsic speed itself, we can rearrange this and make it the upper bound. So write this last inequality entirely in terms of speeds. So in this sense, this is also a way of a result that we can consider a thermodynamic speed limit, and one that's independent of the particular dynamical model we're interested in, or even the particular driving protocol. And it can be extended to a number of other quantities relevant in stochastic thermodynamics. We looked at a number of them in our paper a couple of years ago. And the interesting thing in looking at all of these is that there's a result that seems to draw a nice parallel between stochastic dynamics and quantum mechanics, where we might have Ehrenfest's equation of motion, which turns into this equation of motion that involves the covariance, where the Hamiltonian is being played by the surprisal. Our speeds are very comparable in terms of the various observables. And we've got a time information uncertainty relation that at first glance at least looks different from the one you might know from quantum mechanics and the time-energy uncertainty relation. But in fact, that time-energy uncertainty relation can be expressed as a time-information uncertainty relation if we use the quantum Fisher information. And of course, this result, which was due to Mandelstam and Tam in the 40s, can be rewritten as one of the earliest examples of a speed limit in quantum mechanics. And here we've got a speed limit on a stochastic dynamics. I'll just advertise briefly that we've supported through a collaboration with Wespe, Garcia Pentos, Adolfo Del Campo, and Alexei Gorshkov, realized that this stochastic result can actually be combined with the Mandelstam-Tam result from the 40s and be combined and put into a time information uncertainty relation that's relevant to open quantum systems. So this was a surprising application of something that we discovered we thought was more relevant to stochastic thermodynamics that actually bled over into quantum dynamics. And very recently, I've been working with Sweat-Das, this isn't directly related to stochastic thermo, but I just want to mention for those interested in nonlinear dynamics that we have derived comparable results on deterministic systems. And here the uncertainty is in the initial conditions of the dynamical system and how the system evolves over time. So we posted these papers on the archive if you're interested. So in the time that I've left, I want to mention that something we've been doing recently has been focused less on the thermodynamic costs and more on the thermodynamic benefits side of things, asking the same question: how much time will it take for a certain observable to evolve, but here focusing on the work done on or by a system. So I've been working on this with Erez Aghion, who's done most of this work. And when we went back to the drawing board, in a sense, we were thinking about the nature of time and how we've got these intrinsic speeds, but they aren't directly connected maybe to a period of time that we might want to measure in a lab with a clock, say, running parallel to our system. So we can think of a particular observable evolving over time, many realizations associated with this process, and we can focus on the average of that observable over time. And we can ask, well, when does it reach a value, let's call it C, and give that a particular time TC. So when does this minimum time to reach that value occur, at least on average, in some average sense? And so we defined what we're calling an extrinsic time, the minimum time to reach that certain value. And this is contrasted with our use of intrinsic time so far, which is just more of a heuristically defined quantity using the relationship between time, distance, and velocity, and where we used one standard deviation as a particular distance and our speed being the rate of change of some observable. So we started thinking about this extrinsic time, particularly for the work. This extends to other observables as well, but the work seemed like a particularly important one that hadn't been addressed within the context of thermodynamic speed limits yet. So we're interested in the amount of work that can be done over a period of time, call it big T. And we recognize that the amount of work that can be done actually satisfies an inequality where we can integrate over the absolute value of the rate of work, the power here, and ask, well, when does this reach a particular value C? And Erez recognized that we could actually use the Leibniz rule together with the inverse function theorem and write this down as, well, the rate at which this total time changes with respect to the distance or the amount of work that's done is inversely related to the amount of work, provided it's non-zero. So this we can rearrange. Thank you. We can rearrange and recognize this is actually related to the intrinsic, this is related to the intrinsic speeds. It's just a formal definition of it. The other thing we recognized was, well, we can use the stochastic first law together with the triangle inequality to put upper and lower bounds on this rate. So this gives us a differential inequality that we can integrate and solve if we know these particular, the dynamics of heat and internal energy transfer between the system and the surroundings. So we applied this to a flashing ratchet, and time is somewhat short, so I won't go into the details of how this works. But basically, there's a collection of particles undergoing a Langevin dynamics, and we flash this sawtooth potential, which does work lifting them against this constant externally applied field. So there's some amount of work that's done, and this accumulates, at least in absolute value, over time. So we can choose different models for our dynamics, for the internal energy and for the heat, and we can solve some of those models. So we chose an example of a linear system here and found bounds exactly for the time to achieve a particular amount of work, where we've chosen a particular value of work of interest. But we can choose any value of work that we might be interested in and put bounds on that extrinsic time using these dynamics from the first law. The other thing we did here, to briefly wrap up, is that we recognize that if we look at sufficiently small differences, so look along some work protocol and look at small changes in the amount of work that's done, this inequality that we started with gives us a way of looking at intrinsic times together with the triangle inequality, and we can rewrite the stochastic first law entirely in terms of these intrinsic speeds. So we get these upper and lower bounds, and we've confirmed those numerically with a particle in a driven trap. So we confirm that this bound indeed holds, and we see that this is just sort of a starting point. Some of this is very hot off the presses, but we see that these thermodynamic speed limits we've been working on as a way of looking at both the costs and benefits of stochastic dynamics that we can use as ways of looking more closely at how to design soft matter systems and their dynamical functions. So we're thinking about how to design the dynamics. It's still very early days, but we think that this seems doable within the framework we're developing. And we've seen that the stochastic first law can be rewritten as intrinsic speeds, and with some other work that I'd be happy to talk more about offline with other people, thinking about how these speed limits can be a common language between statistical and mechanical systems and potential way of merging. So with that, I'll stop there, and thank you very much.
Okay, thank you very much, Jason.